I would like you to respond to this learning reflection. Explain how to use function notation to evaluate f of 1, f of 2, f of 1 plus delta x, and f of 2 plus delta x. In writing up your explanation, I want you to be able to apply whatever you say to any function f. So no matter what the equation looks like, your explanation on how to evaluate these should work. That's your task for your learning reflection. For today's presentation, I wanted to focus on what I've seen as a couple problem areas that have popped up in my face-to-face class. I've also talked to some of the students in the online class who are also struggling with this. So I want to do a quick refresher on function notation, how it works. A lot of the challenges I've seen folks have come from not knowing how to effectively use function notation. So let's just look at an example. So suppose we've got a function f of x that looks like this. F of x equals, say, 10x squared plus 5x minus 6. So quadratic equation here. And I want to evaluate this function at various points. Suppose I want to figure out what is f of 1. What this is asking us is, it says when x is equal to 1, what is the corresponding function value or the output value? And of course, the way we calculate that is we just replace everywhere we have an x over here, we're going to replace it with a 1. So we get 10 times 1 squared plus 5 times 1 minus 6. And I can continue to simplify. This is just going to be 10 plus 5. Oops, this was a minus 6. 10 plus 5 minus 6. That all comes out to be 9. So f of 1 is equal to 9. Well, what if I wanted to do something like f of 1 plus delta x? And this is where folks have been having trouble. They see this delta x and they freak out a little bit. Well, the process is the same. So think of what we did up here. F of 1, we just replaced all of the x's by a 1. So we're going to replace all the x's when we're calculating f of 1 plus delta x, all these x's by 1 plus delta x. So it becomes 10 times 1 plus delta x, quantity squared, plus 5 times 1 plus delta x, minus 6. So the key idea is to remember that with function notation, whatever you replace the input value with on the left-hand side, you must also replace the input value on the right-hand side with that exact same quantity. So it can be a 1 plus delta x, it can be anything. Matter of fact, in class, I will often, when students are struggling with this, I just ask, what is f of chocolate chip cookie? And I know it seems silly, but it does seem to help the brain to wrap their heads around it. So this becomes 10 chocolate chip cookie squared plus 5 times chocolate chip cookie, and then minus 6. And then all you do is replace your chocolate chip cookies with your 1 plus delta x. That's helpful for some students. I know it's silly, but it's helpful. Let's come back over here and see what we've got here. We've got 10 times 1 plus delta x times 1 plus delta x again. I'll go ahead and distribute that 5. So I get 5 times 1, just 5, plus 5 times delta x minus 6. And then I will go ahead and multiply these out. So I've got 10 times the quantity 1 plus 1 delta x and then another delta x. So that's 2 delta x's. And then finally a delta x squared, quantity squared, plus 5 plus 5x, 5 delta x rather, minus 6. Now I can combine like terms. Let's see, we're going to distribute this 10 all the way through. So I'll have 10 plus 5, that's 15 minus 6, that's going to give me a 9. So I'll go and take that 9. Let's do the delta x's. Let's see, 10 times 2 delta x is going to be 20 delta x plus 5, so I'll have 25 delta x. And then I'll have 10 times delta x squared, and that will be plus 10 times delta x quantity squared. So f of 1 plus delta x is in fact 9 plus 25 delta x plus 10 times delta x squared. So hopefully this example helps you recognize how to appropriately use function notation, especially when you're working with something like a 1 plus a delta x. So the next thing I want to show is how we would use this sort of thing to find a derivative. Now, I know in the last class, I did teach you the power rule, which allows us to quickly find the derivative, and also the constant rule, but I will go ahead and use the limit definition of the derivative to find the derivative of this function and evaluate it at 1. So I'll go ahead and do that next. So let's just grab this piece and put this off to the side. So we figured out that f of 1 was 9, and that f of 1 plus delta x was 9 plus 25 delta x plus 10 delta x squared. Sorry, running out of space. So I'm going to go ahead and erase this. We're going to use those values later on. But if I want to figure out what f prime of 1 is, f prime of 1 is going to be the limit as delta x goes to 0 of f of 1 plus delta x minus f of 1 all over delta x. That's our limit definition of the derivative. Now, we already know what these quantities are equal to, right? That's what we figured out over here. So a good practice, and I highly recommend this, is when you're solving this type of problem, using the limit definition of the derivative, go ahead and find these values, f of 1 and f of 1 plus delta x, off to the side. Don't clutter the main flow up with those calculations. Do the calculations, get them simplified, and then plug them in. So we'll go ahead and plug them in here now. So f prime of 1 is equal to the limit as delta x approaches 0 of f of 1 plus delta x. That's just the 9 plus the 25 delta x plus 10 delta x quantity squared. And then the f of 1 is just 9. So it's minus 9 all over delta x. Now, with polynomial functions, such as this one, this is a quadratic, it'll always be the case that the constant terms will cancel out. And then we see that here, the 9 minus 9, that becomes a 0. So that leaves me with the limit as delta x approaches 0 of 25 delta x plus 10 times the quantity delta x squared all over delta x. Well, this turns out very nicely because delta x divides in evenly into both of the terms in the numerator. So this becomes the limit as delta x approaches 0 of 25 plus 10 delta x. Now let's think what happens here. As delta x gets closer and closer to 0, this quantity 10 times delta x gets really, really small. Matter of fact, infinitesimally small. So we have 25 plus some super small number. So we can think of this as, well, as we're looking at delta x going to 0, as close to 0 as we want, this entire quantity is going to get it closer and closer to 25 plus 0. You can think of it that way, or in other words, just 25. So the instantaneous rate of change in the function f, this one, at 1 is 25. Now let's just verify that our long work here generated the right answer by using the power rule and the constant rule. So with the power rule and the constant rule, we look up there, we know that f prime of x is going to be, we bring the 2 down in front, so 2 times the 10 is 20x. Then for the derivative of 5x, we're going to bring the 1 down. 1 times 5 is 5, and then drop the exponent by 1. That'll be x to the 0, so that'll just be 5. So if we want to evaluate that at 1, f prime of 1 equals 20 times 1 plus 5, and lo and behold, it matches what we got over there, which is, we expected that to happen. So ultimately, we're going to be using the shortcut method. This is the long and painful method, but it's critical we know this so that we know that we are looking at instantaneous rates of change, that we have a good conceptual understanding of what's happening here as we calculate those values. All right, so I wanted to do that practice there, showing you function notation, how to work with it, make sure you're working with it properly, and also an efficient way to find the derivative using the limit definition of the derivative. Once again, you're going to start the problem by stating the limit definition of the derivative, go off to the side, evaluate those 2 pieces that you need, and then once you've got them simplified, plug them back in and work your way down. All right, next I'll do is another example from the worksheet I handed out on Monday. I want to make sure you guys are able to practice these ideas, find these derivatives, use a projection in terms of a tangent line projection, forecasting into the future. So let me erase the board and we'll try another problem. All right, we are going to work problem number 7 from our handout. I'll go ahead and write the problem up there. This is the handout I posted on Monday. So we're looking at bridge engineering. This is a cubic function on the 7. And the function we're given is this one. H of x is equal to 0.1 x cubed plus 2x squared plus 10. I'm going to put my glasses on to make sure I got that right. That is the correct function. And we're told that h is the height of the arch measured in feet. And then we're told that x is the horizontal position. And ChatGPT did not identify any units for that. We're just going to assume those are also in feet. Again, these are supposedly real models, but we'll see if they actually look right. So let me create a visual for us so we can kind of know what we're thinking about here. We've got some sort of arch. We'll just throw our arch onto this grid system. We'll pretend that's a straight line. And we're measuring from some point a distance. We're going to call that distance x. And then we're going to look at what the corresponding vertical height is. That's going to be our h. So as x varies, the height is supposed to vary according to this. And I just noticed something on my equation. There's a negative sign out here in front. So let me go ahead and fix that. So there's our negative. Make sure I copy that down correctly. That looks right. All right, so our task is, we're first of all supposed to find the average rate of change, if you will. They're calling it average slope here, between 2 x equal 2 and x equal 5. Then we're supposed to determine the slope of the tangent line at x equal 2, and then finally predict the height at x equal 2.1 using that tangent line. So the first thing we need to figure out is what is h of 2 and what is h of 5. So h of 2, we're just going to go up to our equation. We've got a negative 0.1 times 2 cubed plus 2 times 2 squared plus 10. So I've got, let's see, this is 8. 2 cubed is 8 times a tenth. That would be 0.8. So I've got negative 0.8 plus 8 plus 10. Or altogether, what is that? 18 minus 0.8. So that'll be 17.2. Next, I need to evaluate h of 5. Slide this down a bit. H of 5. So same idea. Negative 0.1 times 5 cubed plus 2 times 5 squared plus 10. This is, let's see, this is 125. 5 cubed is. So this will be negative 12.5 plus 25 times 2 is 50 plus 10. So I'll do that again. So I've got 60 there minus 12.5. Should be 47.5. Let's see if I add 12.5 to that. Yep, I'll get back to 60. So I've got my two function values. If I want the average rate of change in this function between those two values, I can just do the change in output, which would be 47.5 minus 17.2 divided by the change in input, which would be 5 minus 2. And that will give me my rate of change. All right, so let's see if we can figure this out mentally. It was 47.5 minus 17.5, which is not that much, but if it was, that would get me right down to 30. But I have to add back that extra. So I think this is 30.3. And I'll do mental math to check. Yeah, 30.3 there, divided by 3 in the denominator. So all told, I get 10.1 units of height, so feet, and those are height feet per position feet. This is foot per foot. Height of foot of height per foot of position. So what does that mean? That means that between 2 feet and 5 feet, the average increase is 10.1 vertical feet per 1 horizontal position feet. That's on average. So if it were to increase constantly for every foot between 2 and 5, that's what that constant rate would be. In reality, look at my visual, it increases by different rates. So this is the average rate over that interval. Our next task is to figure out the instantaneous rate, which is the slope of the tangent line at 2. So we're just at this point. So I'll go ahead and erase this. I'll go ahead and keep that value over there, the average rate of change over there. Okay, so I can calculate the derivative. That's the instantaneous rate of change. Bring the 3 down in front, so I get negative 0.3. Drop the exponent by 1, that's 2. I'm applying the power rule here. Plus, the 2 times the 2 is the 4. Drop the exponent by 1. And then the derivative of a constant is, of course, 0. So this function gives the instantaneous rate of change in the height as the position varies. We're interested in what this is right at 2. So again, I'll replace everywhere there's an x, I'm going to replace it with a 2. And continuing from there, I've got negative 0.3 times 4 plus 8. Well, this is just negative 1.2 plus 8. And I do the subtraction, and I should get 6.8. So what does that mean? This is 6.8 feet of height per foot of position. So right there at 2, a 1 foot increase in position is expected to increase the height by 6.8 feet. Notice that this is a smaller value than our overall average, which we found over there. Okay. So now I know how h is changing right at 2, and I'm supposed to come up with the equation of the tangent line. So remember, we have that h of 2 is 17.2. We're going to use that here in a minute. So I'm going to write my equation of my line. Y minus the y value, which was 17.2, equals our instantaneous rate of change at 2, which was 6.8, times x minus whatever the x value was, which was 2. So this is the point slope form of a line. If you want to move to slope intercept, we can go ahead and simplify it down. So I've got y minus 17.2. I can distribute this 6.8. I get 6.8x. Then I multiply this by 2. Let's see if it was 7 times 2, that will be 14. And then I have to subtract those extra 2 tenths. So I get 13.6. Let's see if that works. 13.6 divided by 2. 13 divided by 2 would be 6.5. 0.6 divided by 2 would be 0.3. And so if I add that 6.5 to 0.3, I get 6.8. So I'm good. All right, so y is equal to 6.8x. And I'm going to add the 17.2 to both sides. That'll be plus 30.8. So this is the function that I can use to predict. This is my tangent line. I'll use this to predict the value. And we're supposed to predict the value at 2.1. So at 2.1, we need to know y is going to be this, 6.8 times 2.1 plus 30.8. Let's just see what this predicted value turns out to be. And I'm going to have to go around my iPad. All right, so I'm just going to bring up my iPad to do that calculation. So I've got 6.8 times the 2.1 plus the 30.8. And I get 45.08 feet. So my prediction is that 2.1 feet of horizontal position, my height of my arch is just over 45 feet. That's my prediction using the tangent line projection. All right, so hopefully that helps.